Okay, it looks like it's time, so it's 9. Let's get started. So the first chapter that we'll start is Waves. This is chapter 15 from textbook. So before we introduce waves, I would like you guys to think about what wave is. So let me hide that for a second. So think about what wave is. So when you hear this word wave, what comes in mind? Yeah, some kind of wavy thing. Okay, that's right. So wave is so basically there are two ways to transfer energy. Okay, so if you want to transfer energy from one point to another point, there are two ways. One is by actually displacing an object. Okay, so let's say you have a ball or something. You have some kind of object, okay? So you want to transfer energy from one point to another point. So one way is by actually applying some force on this, okay? Putting some energy on this, and then you transfer the energy by transferring the object. So you just throw the object and you transfer the energy from one point to another point, okay? So by actually moving the object. And another way is without moving the object. Okay, so there is another way to transfer energy without moving the object, and that is through the waves. Okay, so waves are basically disturbance. So you have some medium. So this is medium. Okay, and I want to transfer energy from this point to some other point. So I can transfer the energy without actually transferring the particles in the medium. So this medium is made up of particles, okay, string particles, and I can transfer my energy. So I put some energy at this point, and this energy would be transferred along this string without actually displacing the molecules in the string. Okay, so I put some energy like this. So my energy is transferred along the string in form of some disturbance. Okay, so I produce some disturbance in the medium, so I disturb the medium, and the disturbance is transferred along the string. Okay, and that's how you transfer the energy without actually displacing the molecules in the string. Okay, and so waves is nothing but it's a disturbance. So you produce some disturbance in the medium, and that disturbance is transferred from one point to the next point. So wave is basically some kind of disturbance that travels with some well-defined velocity or well-defined speed, okay, from one point to another point. So for example, I'll be posting this PowerPoint on Blackboard, so if you don't want to write it, that's fine. You will be able to see this in Blackboard. Okay? So for example, if you drop a piece of stone or something in water, what happens is you disturb the water at a certain point. Okay, so you drop the stone or something on water, it disturbs the medium. Okay, water is the medium, and the disturbance is propagated outward in the medium in form of wave. Okay. So you see these kinds of round shaped structure, that is the disturbance that is being propagated outward. Okay? And in order to propagate the disturbance, you need some kind of medium. Okay? And there is a special kind of wave that requires medium to transfer the energy. Okay? So those waves are called mechanical waves. So we'll talk about another kind of wave where you don't need any medium. Okay? So you can also transfer energy or waves without any medium. So we'll talk about that later. But for now, we'll talk about the waves that require medium to propagate from one point to another point. And those kinds of waves are called mechanical waves. Okay? So mechanical waves are the waves that require medium to be transferred from one point to another point. So basically you disturb a point in the medium, and then that disturbance is propagated in the medium. So let me show you a simulation.
Control included.
So you see here, so basically you produce some disturbance in some medium, and then the disturbance is propagated in the medium. Okay? So here is example. So here is the medium, this is the fluidity. Okay? So this is the medium. I'm going to produce some disturbance at this point, and then the disturbance would be transferred along the medium. So here is the disturbance. So that disturbance travels in the medium. Okay? And that's what wave is. Likewise, when I hit this tuning fork, so this is tuning fork, what happens is when I hit the tuning fork will vibrate. Okay? It will vibrate, and as it vibrates, it disturbs the medium. The medium here is the atmospheric molecules, okay, or air molecules. So the air molecules will be disturbed, and the air molecules will transfer the disturbance from this point to your ears. Okay? So when I hit this, it disturbs the medium. Medium is the air molecules, and the air molecules transfer the energy from this point to your ear. So in order to produce the disturbance, you need a source. Okay? So there is a source related to disturbance. So in this case, this tuning fork is the source. Okay? So when I hit this tuning fork is the source of the disturbance. When you drop a piece of rock in water, the point where you drop the object, that is the source of the wave. So if I drop this object in water, so the point where it lands is the source. So you need some kind of source to produce wave disturbance. Okay, so once you produce the disturbance travels outward, okay, at some defined speed. Okay, it travels at some speed. So for example, if I produce disturbance at this point, that disturbance will travel at some speed, well-defined speed. It may be 1 meters per second, 2 meters per second, 3 meters per second. Okay, so at some some particular speed. So if I shake this, that disturbance travels at some speed. So there's always some well-defined speed with which the disturbance travels in the medium. Okay? And one very important thing here you need to keep in mind is when you disturb the medium, what you do is you transfer the energy, okay, to the medium, but not the medium itself. Okay? So the medium has, like I said before, particles or molecules. So the molecules remain at the same location. The molecules do not get transferred. What is being transferred is the energy. Okay? I'm transferring the energy from one point to the other point. But the molecules in the string is unchanged. Okay? They remain at their original location. Okay? So like in the previous simulation, so if I go to the simulation again, so you see here very clearly let's blow it up a bit. Look at this red dot, okay? So what happens is when you disturb this medium, the molecules move back and forth, okay? Back and forth, back and forth. So when you disturb this medium, it moves forward, it transfers its energy to the next particle, and then it returns back, okay? And then moves forward and backward, forward and backward. But it doesn't go forward along this medium. Okay? It remains at its original location. So there is no transfer of the actual medium particles. Okay? So the medium particles remain as it is. What is being transferred is the wave. Okay? So you see the wave is being transferred along this direction without actually transferring the particles in the medium. So a wave transfers energy, but it doesn't transfer any material or substance outward from the source. It does back and forth, back and forth, back and forth, but it doesn't move away from that original location. Like I said before, we have this mechanical wave where you transfer the energy by moving the particles back and forth in the medium. But there are also waves that do not need any medium to transfer the energy. For example, electromagnetic waves. Electromagnetic waves transfer energy without needing any medium. For example, sunlight. Okay, so the sunlight energy is transferred from sun to the earth without needing any medium in between. So we will talk more about these electromagnetic waves after we finish. Electricity and magnetism chapter later, towards the end. Okay? But for now, we just need to know that there are waves that transfer energy without needing any medium. Okay? For now, we'll only focus on mechanical waves. Okay? So mechanical waves are the waves that transfer the energy to the medium. But in case of electromagnetic waves, there is no need of medium. Again, we'll talk more about this later. Okay, so there are two types of mechanical waves. First one is transverse wave, and the second one is longitudinal wave. So transverse wave, in case of transverse wave, what happens is when you disturb the medium, okay, when you disturb the medium, what you do is you move the molecules in the medium up and down. Okay, so the disturbance you produce at this point travels along this medium. It's traveling that way, okay, to my left. From your perspective, it's traveling to the right. It's traveling to the right, and the molecules in the medium is moving up and down. Okay, so what happens is the molecules, this part of the molecules move up. Okay, it pulls this one up. It pulls this one up. Pulls this one up, and then when I move this down, this one moves down, down, down. Okay, up, down, like this. So, in case of transverse wave, what happens is the molecules move up and down, okay, which is perpendicular to the direction of propagation of the wave. So the wave is actually moving this way, okay, whereas the particles in the medium is moving up and down, perpendicular to the direction of propagation. So transverse waves are the waves in which the molecules in the medium move up and down or perpendicular to the direction of propagation. Okay? So for example, so in this case, you see the particles are moving up and down. Okay, it's up and down, up and down, up and down, and the wave is actually propagating along this direction. Okay? So the wave is propagating along this direction, whereas the molecules are moving, or the particles are moving up, down. That is perpendicular to the direction of propagation. So this is transverse wave. Whereas another kind of wave called longitudinal wave. See here. In case of longitudinal wave, the wave is propagating along this direction, and the molecules are also moving along the same direction. It's doing back and forth along the same direction. Okay? So each of these molecules, they move back and forth like this, in the same direction as the direction of propagation. Okay? So in case of longitudinal wave, the particles move back and forth along the same direction as the direction of propagation of the waves. Whereas in the transverse wave, they move up and down perpendicular to the direction of propagation of the waves. So what are some of the examples of transverse wave? Can you guys think of any transverse wave example? One example is the example that I just showed. So if I produce disturbance in this rope, the particles in the rope moves up and down, and the wave travels along this direction. So the direction of movement of the molecules is perpendicular to the direction of propagation of wave. So that's the transverse wave. So this is transverse wave. Okay, so that's transverse wave. Longitudinal wave. If I move this slinky like this, that's longitudinal wave. Okay, so the medium, the molecules in the medium is moving back and forth along the same direction as the direction of the wave. So the wave is moving that way, and the medium is also doing back and forth in the same direction. Okay. So let's focus a little bit more on the mechanics of how the waves are produced. By the way, one more example here. So during the earthquake, usually you get two kinds of waves. One is called P wave, primary wave. Primary waves are longitudinal waves. Okay, so when you get primary waves, the primary waves shake the earth horizontally like this. Okay, so that's the primary wave. So primary waves are longitudinal waves. It moves the ground horizontally. Whereas there's another kind of wave called S wave, secondary wave, in which the motion of ground is vertical, moves the ground like this. Okay? And this one is more destructive than the primary wave, because this can lift the buildings. Okay, so secondary waves can lift the building and then it just drops the building. That could destroy the structure pretty easily. So primary waves are more destructive. Sorry, secondary waves are more destructive than primary waves or P waves. How about ocean waves? Are they primary waves or secondary waves?
Neither.
Neither? Or both?
Maybe both.
So let me show. Sorry for going back and forth within this simulation. So you see here, ocean wave has both primary wave, longitudinal part as well as transverse part. So this is the water wave. So you see here, the molecules are moving up and down as well as back and forth like this. So it's moving up and down. You see here it's down, going up, down, and it's also moving back and forth, okay? Forward and backward. So the combination is, it moves in a circular path. Okay? This is also called circular wave. So circular wave is combination of transverse wave and longitudinal wave. So this is up down is transverse and backward forward is longitudinal wave. And ocean wave is the combination of both. Now, as you go deeper and deeper, the circular waves get smaller and smaller. Okay, so as you go closer to the surface, it gets bigger and bigger. Because there is less movement in the below of the ocean, so there is smaller circular waves. Okay, so let's talk a little bit more about this. So now, when I pull this string up at this point, what happens is I pull the particle immediate to my hand. Okay, so when I move this up, I move this particle up. Okay, and that creates tension in the string. Okay, so it creates tension in the string. It creates upward tension, and because of the inertia, okay, so this piece of string also has some inertia. So because of the inertia, there is also this downward tension. Downward tension tries to prevent the motion, whereas this upward tension prevents to pull it up. So there is two types of tension that acts at the point where you apply the force. Okay, so when you lift this, there is this upward tension, and there is also this downward tension, and the net tension is upward. Okay, so there is more force in the upward direction than downward. So because of the inertia, it's trying to pull this down, but my hand is trying to pull it up. Okay? So there are two types of forces acting at a point. Okay, and because this is greater than that, so the net force is up, and that net force pulls it up. Okay, So it pulls the string up. Now, at some point, you would be pulling it down. Okay, so you first pull it up, and then at some point you would be pulling down. So when you pull it down, there would be more tension down and less tension up. Okay, so when you're pulling it down, there's more force down than up. So up is the inertia tension, and down is your hand tension. So hand tension down is greater than up tension, so that produces the downward force. So downward net force, and because of that, these particles move down. So the consequence here is here. So when you're moving it up, okay, you move the string up. Okay. So when you move this up, it pulls this part up. Okay, this part up. This part pulls this part up. This part pulls the next part up. Next part up. Next part up. And as you pull it down, it pulls the next part down. Next part down. Neighboring point down. Okay, and the consequence is it produces this kind of curvature. So the curvature is exactly same as the movement of your hand. So you are moving your hand up and down. So that creates this kind of curvature. So up and down. So let's talk a little bit more in a different way. So let's consider the particles in this string. Okay, so consider that the string is made up of number of particles, like 1, 2, 3, 4, and so on. So when you pull this part up, it pulls particle 1 up. Okay, so the particle 1 is pulled up. And this particle 1 will pull particle 2 up. And this will pull this one up. Okay? And when you pull this part down, that pulls this one down. And then in turn, this one pulls this one down. So when this is going down, this would be up here. So when this is going down, this is up here. And this particle pulls it down. And this one would be pulling this up. So this one would be here at the top. And this particle would be pulled down by this. This will pull this one down. Okay. So basically, this kind of curvature is due to the internal dynamics of these molecules. Okay. So they pull each other in different directions. And because of that, you get this kind of curvature. So basically, when you produce a disturbance, that produces a pulse, and that pulse moves along the string. Okay. So there is an example of how the waves are produced. So here is the medium, and when I produce some kind of disturbance at this point, so this disturbance will be transferred along the medium without actually moving the medium. So the medium remains at its original location. It doesn't move forward. It does up and down, but it doesn't move along this medium. So I produce the disturbance like this, and it's transferred in the forward direction. Okay. So this is a transverse wave. So the waves are transferred along this direction, whereas the medium, the particles, these are the particles in the medium. The particles are moving up and down. It's going up and down. So when I pull this up, it pulls the next particle. the next particle pulls the next particle, next particle pulls the next particle, next particle. And then when I move this down, it pulls the next particle down, next particle down, next particle down, like that. Okay? So there is internal dynamics within the medium that produces the wave. So again, when you produce the wave, there are two types of tension. One is upward, the one is downward. So one thing you need to keep in mind is when the wave is hitting a particle, so this is a particle in the medium, and the wave is approaching the particle. Okay? So the wave is going this way. When it hits the particle, what happens is this part will pull it up, and there is also this part that tries to pull it down because of the inertia of rest. Okay? Because inertia tries to keep it at rest, at its original state. So there is this downward tension of this part, and there is this upward tension, it's trying to pull it up, and the net is up. So when the wave hits the particle, at the very moment when the wave hits the particle, the net force is up. Okay, the net force is upwards, and because of this net force, this molecule moves up. Okay, or the particle, whatever you want to call, molecule or particle, it moves up, and as soon as the wave, the maximum of the wave passes through the particle, so that's the maximum of the wave, and the maximum of the wave passed through the particle. Now it is being pulled down. Okay, so this part pulls it down, and this part tries to retain its original state. Okay, so there is this tension of this part is trying to pull it down, and there is tension here that is trying to restate its original state. So there is this tension, upward tension, downward tension, but this part of the tension is bigger than that tension. Okay? So this tension is bigger than that tension. That means the net is down. Okay? Because this downward tension is bigger than upward tension, so the net tension is along the downward direction. It's like I'm trying to pull this, exerting two forces. Okay? So I'm applying some force in this direction and applying some force in this direction. If the force along this direction is bigger, then it will move along the force where there's bigger force. Okay, so it tries to move along the direction of bigger force. Same thing here. So this force is bigger than that, so it moves down. Here, this force is bigger than this force, so it moves up. So particle moves along the direction of that force. So here is a question. So the wave is going from left to right, so it's moving this way, and there's a particle here. So at this point, the wave hits the particle. So which way would the particle move? Will the particle move up or down, right, left, or it won't move? So look at here. So when the wave hits the particle, upward force is bigger than downward force. So net is up. When the wave passes the peak of the wave passes the particle, downward force is bigger than upward force. So it moves down. So now you see, is the wave just hitting the particle, or has it already left the particle? So forget about this part. So the wave is moving this way. So this wave just hit the particle. So there's this upward tension, there's downward tension, and this upward tension is bigger than downward tension. So it moves up. Okay. Okay. So the next one is sound wave. Okay. So we'll talk about sound wave. Sound wave is an example of longitudinal wave. Okay. So this is an example of longitudinal wave. So how do you produce sound when you play some kind of music?
Vibration.
Yeah, vibration of the speaker, right? So you have the speaker has this some kind of paper, very thick paper. You vibrate that. When you vibrate that, what it does is it compresses the air particles. Okay, so the air particle is uniform right now. When you produce the sound, it pushes the air molecules in the forward direction, and that push will produce some kind of compression. Okay, and the compression is the disturbance that you transfer in the medium when you produce the sound. Okay, so in sound, transfer of sound, you actually transfer the compression of the molecules, air molecules. So let's see a picture that will make it more clear. So here is the picture. So when you produce the sound, you disturb the medium, okay, immediate to the speaker. When you disturb the medium, these molecules will move forward, okay, and that will push the next molecule forward. That will push the next molecule forward. Okay. As soon as it moves to the maximum displacement, it will come back, and it will move this way, and then back and forth, back and forth. It's not moving forward, it's just doing back and forth. Okay? And you will see that at some point, you will see the molecules are compressed. Okay? They are close to each other. So it forms a compressed region. This region is called compression. And it also forms a region where there's less molecules. So this is called rarefaction region. So there is compression region and rarefaction region. Where the molecules are dense, that's compression. Where the molecules are less dense, that's rarefaction. And you actually transfer this compression along the medium at some speed. Okay? And that's how you transfer the sound. And when this disturbance hits your ear, you have eardrum. It vibrates your eardrum, and there are nerves in your ear. There are 3 types of bones. It vibrates the bones, and it sends the signal to your brain through some kind of nerves, and your brain interprets the sound. So let me go back again. So I'm doing back and forth all the time. Here. So you see here, there is compressed region. Okay, you see there is compressed region, and there is less dense region. So when it's moving back and forth, it always forms compressed region and less compressed region, or less dense region. So the compressed region is compression, and less dense region is rarefaction. I can show that in this slinky also. When I move this back and forth, you will see compressed region and less compressed region. You see that? There's compressed region. And there is less dense region. Okay, so the speed at which the sound or the longitudinal wave travels does not depend on size or shape of the pulse, or how big the size or shape of the pulse is, how big it is. Okay? I can I can produce a small pulse like this, or I can produce a big pulse like this. Okay? So this is a bigger pulse. Or I can also produce smaller pulse like this. So the speed does not depend on the size of the pulse. Okay? No matter if it's a big pulse or a small pulse, that won't affect how fast it's going to move. Or it doesn't depend on the shape of the pulse. Okay? Or how the pulse was generated, or how fast it has, or how far it has traveled. So, but it depends on two things. Okay, the speed with which the wave travels along the medium. Okay, so this is true for transverse as well as longitudinal wave. It's true for both. So, how fast the pulse travels through this, it depends on two things. Okay? First one is the thickness of the string. Okay? Thickness of the string is expressed in terms of linear density, which is mass over length. Okay? This is called linear density. Higher the linear density, thicker is the string, or denser is the string. Okay? So, how fast the wave travels through this string, it depends on the density of this string, or how thick it is. Thicker the string, less is the speed. Okay? Slower it travels through the string. So, the speed and linear density are inversely proportional, not exactly inversely, but square of inversely proportional. I will show you that relationship later, but you can think of that in this way. So as you increase the thickness, the wave will travel at lower speed. Okay? So the speed and thickness are related in opposite way. Another thing is the speed depends on the tension. Okay? How tense the string is. If it is really, really tense, it will travel really, really fast. Okay? It will travel really fast. If it is less tense, the speed would be less. Okay? So greater the tension, greater is the speed. Okay? Like when you play guitar or some kind of musical instrument, greater the tension, more is the speed of the sound. More is the speed of higher the speed of the wave you produce. Okay? So it depends on two things. One is tension. Okay? Higher the tension, higher the speed of the wave. Higher the density of the medium, less is the speed of the wave you produce. Okay? And the relationship between string, the speed, tension, and density is given by this formula. Okay? So this is the speed of the wave that you produce in the medium. That's the tension of the medium. That's the density of the medium. And the reason speed is oppositely related to the density is denser the medium, more inertia it has. Okay? More inertia it has, more inertia of rest it has. That means it tries to, the denser medium tries to oppose the motion, resulting in less speed. So, denser the medium, less the speed of the wave in the medium, because of the inertia of the medium. Okay, so let's see this question. So you have two media of same thickness, and you have two waves. So which one would be which one would be
C.
higher? Which speed would be higher?
C.
C, right? That's right. Because the thickness is same, and the tension is also same. Okay, so same stretched. Same stretch means same tension, and the thickness is also same. So both are same for both the strings. So V would also be same. Okay. Again, like I said before, the shape of the wave doesn't matter. Okay. So the shape of the medium doesn't affect the speed of the wave. Only these two things affect the speed of the wave. Okay, let's look at one more. So you have a medium where the speed is v. Now if you want to make the speed twice as fast, what you need to do? We need to increase the tension by a factor of 2 or 4?
4.
4, exactly, because there is a square root here. So because of the square root, if you increase this by 4, this would be increased twice. Okay? Because when you pull the 2 out, when you pull the 4 out, it becomes 2. Does that make sense? Or I can show you. So V1 is T over mu, okay? And we want to get, let's say V2 is 4 T over mu. So we pull it 4 out, and it becomes 2 T over mu, and this is V1, 2 times V1. So in order to double the velocity or speed, you need to quadruple the tension. Let's see this numerical problem. So this is the application of what we just learned. So the spider wave has the density of 1 times 10 to the negative 5 kg per meter, and it's under the tension of 0.4. Okay. If the insect is 30 centimeters from the spider, how long will it take for the spider to find out? So here is the, let's say this is the spider wave, and the insect is somewhere there. Okay? So when the insect moves, it sends the wave. Okay? So let's say the insect is here. When the insect moves, it sends the wave along this wave, and at some time later, the spider will sense the wave. So how long will it take for the spider to sense the wave? So first you need to find the speed at which the wave travels. Okay? So when the insect produces the wave, it travels along this direction. And what's the speed of that wave? Speed we know is given by this formula. Okay, so that's the speed. Okay. So that's the speed of the wave produced by the insect. And the insect is 30 centimeters from the spider. Okay, so the distance between the point where the wave is produced and the spider is 30 centimeters. So the time it takes to reach to the spider is distance over speed. Okay, so that's the formula that you learn in physics 1. Velocity is distance over time, so time would be distance over velocity. And the time is given by distance, which is 0.3 meters, that's the distance, and that's the speed. So 1.5 milliseconds, okay? So that's pretty fast, 1.5 milliseconds. So the wave travels very, very fast in the wave. So we are out of time. I think we'll end today's class here. If you guys have any question, I can answer your question. Otherwise, that's all for today.
Is the formula specific to any units? And you have to absolutely positively meters, or is it just proportional?
It needs to be the standard unit, like meter, second, kilogram. Yeah. Please use the standard unit, metric unit.